Recording group together. Recording group. Starting.
Am I audible? Is my voice clear, please? Can you confirm? Yes, thank you.
Assalamu alaikum. Morning, everyone. I hope everyone is fine. My name is Hassan Ijaz Malik, and I am working as a senior design engineer since past 2 years at with RW Private Limited. My core area of interest specializes in development of receivers, RF front ends for radars. I have worked with ESA radars, pulse Doppler radar systems in the past, and currently I'm working at RWR in the fields of alien and current receivers. We have direction finding receivers. We have a team of dedicated engineers. We work on different types of engineers for diverse applications. Today's webinar is on the RF front-end design for high sensitivity receivers. In today's session, we will go through different aspects of receiver design. My my efforts will be to share the inside design and implementation level knowledge that I have gathered since the past around 7 to 8 years working in the industry. So how to analyze different parameters without going much into the mathematics. So first, the today's session is I have divided into three different subsessions, and these are not the mandatory ones. May change. First a basic introduction to receiver design, where actually is a receiver design. We then basic terminologies, the design parameters. Then in session 2, we will mainly focus on the super heterodyne, the famous super heterodyne receiver architecture, where you have two diverse mixing stages, translating frequencies from one band to another. And in this session, I also brought an installed version of Pathwave system. We will go through the software, and it's we'll set up a basic configuration of a system view, super heterodyne receiver in the software. Then actually I will share a practical design example that I have been implementing since the last 2 years, and what results we have achieved there according to customer needs and requirements. Then in the session 3, mainly I will be discussing the results and measurements, different aspects, the crucial aspects when a receiver is being delivered for some application, the gain equalization, noise figure, phase noise, effect, LO phase noise, how they are measured and how actually they contribute. So at the end, question and answers will be welcome from you. So what we won't be, because the topic is so much diverse, and there are a lot of things that could not be touched in a 3.5 session or 3-hour session. So we won't be going into information or modulation, demodulation theory, automatic gain control, or STCs in receivers. Then we won't be addressing or discussing much about ADCs at present, because ADC is a part of receiver when you get the data into the digital domain. Then the role of EMI in your design pathway. Then first, starting the generic communication system we have studied over the years, the information starts from the source. it may be bits, it may be audio, it may be data, image, anything. Then you process and streamline the data into a modulatable format, into a modulation schemes. Then you have an RF front end. They might be a digital in the past information processing. I have seen a radar system where all the things were implemented of the using discrete electronics, capacitor resistors, tie rods, SCRs. So now that all goes to a digital board. So then after that we'll discuss. Then after there is a transmission setup where you actually you have an antenna, you have an amplifier. If you are frequency translating, you might be moving from one band to another using frequency mixer. So there's a transmission setup. Then is a propagation channel. Propagation channel has its own effects. It may add delay, noise, channel effects, propagation delays, multipath, different aspects of the propagation channels contribute toward the system, the received signal properties. Then you have a reception system, mainly a receiver. Then, of course, you have a reverse information processing that was done in the processor. If it is a radar system, that all will be at the same place. If it is acting as a communication system, full duplex, half duplex, any mode, it will be a distance communications. So at the end, the information destination information arrives there. You decode there as a picture, audio, web page, anything. So today, our topic of interest will be reception part. That is the receiver. Our receiver comes in different forms and factors, different applications. Without going into detail on the more on the communication system, we will now move toward different receivers architecture that are being conventionally used in different applications. You find them in FM radios, you find them in AM radios, TV antennas, digital dish, satellite communication, mobile communication, 5G, 4G, upcoming 6G, radar communications, ELINT. So, and although the main spectrum of interest today we will be talking about will be around 3 to 30 or maybe 40 gigahertz if we include the upper band, upper K band. So this is the main frequency of interest. Usually, most of the systems are being developed. There are systems in LF, VLF bands for long range, long distance communication. Like I have studied a system based in ELF frequencies that can communicate around 6,000 to 7,000 kilometers for communication with submarines. So those are the lower frequency bands. So today the topic of discussion will be around 3 to 30 mega, you can say, through to 30 giga or 40 giga if you include the upper end edge of the K band. So now, moving toward the classification of radio receiver architectures, different types of radio receivers that are available and being implemented. The first one is the homodyne receivers, heterodyne receivers, super heterodyne receivers that you can find nowadays in most of the applications being used. Then the upcoming trend of direct sampling receivers that with the advent of ADCs, they are up in the market, RF SoC system on chips. Luckily, I will later share. We have seen a system of direct sampling receivers as well. So first, we go to the homodyne receiver architecture. In a homodyne receiver architecture, you receive a signal from the antenna. You have a band pass filter. Then you have a LNA frequency mixer, channel select filter, low pass filter, then a baseband output. In a homodyne architecture, the main difference between other is the frequency translation. When you pass the signal to the mixer, as you all know, why we need frequency translation in our RF systems, because managing a bigger antenna is a different is a different type of problem. So moreover, when you are working at lower frequencies, you can have less data communicated, less data transferred. So as you move towards high frequency, you can have more data transmission efficiency, and of course the antenna size is reduced. So you can compare the AM radio size and the FM broadcasting station size. There is a lot of difference between them. Now, in case of pointer have to. Now, if you see the antenna and the band pass filter, or as you see on the screen, the antenna followed by a band pass filter, then LNA, then mixer. These are the primary components. They can be less or more based on the user requirements. As we move towards the progress towards this session, I will share with you the actual design I have implemented and the results. You will find out that there are a lot of practical things that we accommodate into our design at a later stage. So what happens in a homodynamic receiver? Your modulated frequency band, for example, this is for example, is 1.2 to 1.5 gigahertz, this FC band. So it after mixing, it will be translated back to DC to some. I'm showing both side bands, but actually practically you only use one side band, single side band. So DC to some frequency. So that's in any receiver, when the conversion is in this way, that is known as a homodynamic receiver architecture or zero frequency, zero IF frequencies. So that architecture is also used in different systems. With now the current advent of modern ADCs and then with better sampling rates, this you may find this system as well in many of the new receiver technologies. So finishing this slide, so when you translate the FC near zero, that is known as homodynamic architecture. Now, for practical application, one of the famous applications of homodynamic receivers is FMCW radars. In the modern vehicles, even the radars operating at 77 gigahertz or the lower 60 gigahertz band, they also work as a FMCW radars. They have a homodynamic architecture. Here you can see this is the main oscillator that generates the frequency. Then it is coupled via hybrid coupler to a hybrid coupler or a 10-20 dB coupler coupling to the LO mixer. This is the transmission path. Then maybe this is an amplifier or isolator. Then transmitted, reflected back from the target, received by the antenna. I'm talking about now this receiver part, LNA. Then again might be isolator or isolator to isolate the RF from the LNA. Then there's a mixer, then an IF amplification stage, then the data acquisition stage. So in this FMCW radar architecture, you can see this is implemented on homodynamic architecture. And traditionally, it is a design for FMCW radar. The reason because in FMCW radar you couple. This is your transmitted signal that is going out, and you couple its own reference with the frequency mixer. So your transmitter and the receivers are co-located. You have you can directly translate that frequency to a lower frequency near DC. So that is another example of FMCW radar. That is also a simpler version, or you have a modulation scheme. Ramp generator, this VCO voltage control oscillator. Back in 2014 and 13, I implemented this topology of the radar system. You can see this is a power amplifier, it goes out, there's a coupled power to this mixer. So there's a single stage mixer, and that single stage mixer will implement the received frequency will be near DC. So what happens is in an FMCW radar system, you have DC to some few megahertz of beat frequency. The higher the beat frequency you receive at the IF, the more distance the target will be. As the target comes close in, so your DC your frequency gets closer to your DC point. So becomes a problem, because this becomes a problem in this architecture, homodynamic architecture, which is a major disadvantage of this topology. That in mixer, when the phase of the transmitted and received frequency becomes same, then it produces a DC shift. So at the ADC, this becomes a big challenge to mitigate or to cater that DC shift. So that is the major disadvantage of homodyne architecture. So in practical application in radar systems, when you miss a small chunk near DC, if you miss a small chunk near DC, so you are missing the target information in that range. That is actually termed as the blind range of FMCW radar system. That was the receiver. Then, as stated there, these are the near information loss near DC. So such another problem that occurs due to DC leakage, effective detection process. I am sharing with you that there's a blind spot of the radar system where it cannot see. So that is known as a blind range of radar system in FMCW radar. In a pulse radar, the blind range is actually the transmission side, transmission time of the radar pulse. So first we talked about homodyne architecture, near zero receivers. Then we move towards the heterodyne architecture. In heterodyne architecture is just different from the homodyne in a way that you don't translate near zero to avoid the DC. To avoid DC part, you don't translate it the frequency. You translate it in some higher IF. But this design has its own challenges as you move it farther from the DC endpoint. So you get closer to the image frequency of the there will be an image on this side and another on the other side. So you need to avoid that. So as you move close to the DC to get farther away from that image frequency, you need a high Q band pass filter. So at this point to reject the image. What is the practical aspect of that? That practically, as you move towards lower frequencies, higher Q filters, they may be larger in size. Then you won't find assembly components for that. You will have to accommodate maybe LC, bigger size LC filter, or you have to go through different trade-offs based on which topology you decide, which band pass filter, which frequency plan you have to. So the main difference between heterodyne and homodyne was then heterodyne you don't go near DC to avoid the DC loss, but it has its own trade-off. Like I have already stated, the heterodyne receiver, you have high Q filters for the lower IF frequencies. That is the challenge to make. Then image frequency rejection, if you don't get a high Q filter, and then you have more stringent filtering requirements because you might be compromising over the filter bandwidths. Then the third and the most abundantly used nowadays filter topology is the super heterodyne receivers, where you have two different local oscillators, two different frequency transmissions. Today, the later on example and the implementation we will be sharing will also be based on super heterodyne receiver architecture. It may seem more complex than the previously two discussed designs, but it has its own benefits, and people do use. It's a lot of the time you can find it's in your FM receivers, modern FM receivers. They are based on super heterodyne receiver architectures. Then a lot of other applications where it is super heterodyne receiver is commonly used. In a super heterodyne receiver, you have two stages. First, it is an RF stage. You have an input RF signal, band pass filter. Then you have first mixing stage. In the first mixing stage, based on the RF input bandwidth, your first local oscillator will be tuned, and then there will be first IF signal. The first IF signal, it might be high side injection or low side injection. By high side injection, by low side injection, I mean when you have, for example, if you have you are interested in capturing an RF signal of 100 to 1 gigahertz, then and your LO is in the range of 3 giga, maybe 2 giga to 3 giga. So your LO frequencies are higher than the RF frequencies. That configuration is known as a high side injection. And if the LO is lower than the RF, then it's known as a low side injection. Both have their own benefits and trade-offs. I will share it later on in a practical design. So how that behavior of a high side or low side injection affects the performance of the receiver. So let's assume, for example, this is a tunable oscillator. a signal 1 mega to 1 giga is coming in. So this filter will actually, if it is a high side injection, LO is between the range of 2 to 3 giga. So this will, we have a fixed frequency, this path. This will have a maybe high side injection that will produce a higher, since you know that after mixing there are two side bands, upper side band, lower side band. So you might be accommodating the upper side band, and with the upper side band, maybe centered at, let's assume it is centered at 3 giga. So this LO will be tuned automatically. Then you can sweep all the frequency bands. So practical essence will be when I will share the design, then you will have more understanding of the process. Then the second stage mixer, actually you can the first stage is up converted, then you can down convert the band of interest to an IF stage. In a heterodyne receiver, the main distribution of gain, the another aspects of any receiver, any signal you might receive, you want to receive, you want to amplify that signal. So a basic rule of thumb or a better implementation approach is you usually don't put a lot of gain in the first stages. You only put low noise components as low noise as possible in this part before the first mixer. And thus between the two mixers, you put as much gain to accommodate the conversion loss of the mixer. If mixer your passive device, it is basically a diode-based rectification component mixer. You can see mixers. They have a conversion loss. These are passive devices. Practically, they are available active mixers as well. They have their own challenges, but usually we prefer using where we have an LO drive level. Okay, then we use passive mixers. So getting into the details of the mixer is another big subject. I can state that the best mixers are the Marquee Mixers, the company. So we use we use a lot of their mixing products. So mixer in all the frequency transmission devices where receivers are frequency translating from one band to another, mixer is one of the, I will say, the key component of your design. If you don't pay much attention to the selection of a mixer, then eventually you will your information will be lost. You might have spurs at the later stage. You might have intermodulation distortions. So selecting a mixer is also a big challenge. In a super heterodyne architecture,
किस कंपनी के रिसीवर मिक्सर्स यूज कर रहे हैं आप?
Marquee Mixers,
मार्केट में
बहुत मशहूर कंपनी है Marquee. Basically, its name is changed now to Marquee Microwave. Now they make a lot of other things as well, but the prime products where they started was Marquee Mixers. So in a receiver chain, the second stage mixing is usually to bring that back to a sampleable standard where you can actually sample the signal to every system might have different ADC requirements, different data rate requirements, because when you have a data stream, for example, your IF signal at this point, this is an audio amplifier, but let's assume that your IF signal is centered around 3090 megahertz. Then putting in a high speed ADC 1300 MSPS samples or to that you will need extra effort at the digital end to handle that data. For instance, I can quote you and share you an example. Recently, we have been working on a system that has an IF frequency centered around 700 to 1200 megahertz. So we had to use an ADC for around 1300 MSPS samples with IQ sampling. So when the data chunk was from the FPGA, FPGA was controlled, ADC was controlled by an FPGA. When FPGA send that data to the PC won't be handling that. So from that, I think 11th or 12th generation system, they moved to GPUs. So on the GPU tunnel, so the data was around 6 to 7 gigabits per second. So they needed PCI slots to handle that much data. So I'm not talking about that part at present, but that is another aspect of a collaboration from the digital team. Wherever you are working digital, you need to get an input from the digital team as well. The hardware they have, how much data they can handle, and how much ADC sampling frequency could be maintained, and which ADC to select. So that is not the topic of discussion at present, but that is also linked to a receiver, because At the end, when you sell a product to a customer, they need a full-fledged solution. They just need a display on the screen. So it's very important to select your IF frequency accordingly when you are actually planning all the system. I can share you an example of one of my implementations where we have 100 to 1 gigahertz input signal. Then the tuning LO that would tune was around 2 to 3 gigahertz. Then at the center frequency was 20 to 50 megahertz. 2 giga 50 megahertz. Then it was again down converted to around 188 megahertz with 100 megahertz bandwidth. So at this point at IF, it was a 100 megahertz bandwidth signal with a center frequency of 188 mega. So that could be easily sampled by 600 MASPS or 500 MSPS. That also depends for which application you are actually targeting. That system is mainly for communication intelligence application. We don't not interested much in the frequency shift. You are more interested towards what actually, because in the communication signal there is a lot of data modulation, digital bits, PSK, ASKs, or QPSK, QAM. So there will be a different requirement for ADC for this model. Now I can share you if there is another system, for example, for RWR, radar warning receiver application, where you are only interested in the envelope of those signals, because for the pilot, you have to usually in an aircraft, when it is installed in an aircraft, you have to tell the pilot for incoming radar painting you from the ground or a missile chasing you. You have to inform the pilot within less than a second. So in that case, this architecture doesn't suit. So what they do is they have direct video receivers. They directly detect the incoming pulse, not interested in the phase. There are two separate systems. One is FMR, that is measuring the frequency of the incoming signal. Then there is another that is actually extracting the information of video out, or the information in the amplitude. Then there's the third system closely placed that actually extract the information of phase. But the first two systems, the FMR and the video out signal, they bring the pilot to the scope. Those two parameters are directly fed to a system that actually compares to a library, that library, and just on the pilot screen it says first it is a threat mark, okay, from this quadrant. Actually, on the aircraft, you also need to tell the pilot which direction you have received in RWR. RWR is primarily the prime product of my company, the present I'm working on. So in the first attempt on the pilot, it comes, there's a target. After, I think, 1.5 seconds, it comes from the threat library. It has been first, okay, this type of threat it is. So in that configuration, this system can't work, because you need a very quick response and a very, very accurate one. So that system, that configuration for particular, this system is for ELINT application or comment application. We are gathering the data and you are logging it back. You are making libraries to actually, and you are also behind your safe within your territory. You're not in any enemy territory. You want to gather information. So our later on example will also be related to that. The receiver I have implemented. So coming out of heterodyne receiver, so this is a two-stage conversion, two-stage frequency translation receiver, where you receive an incoming signal, then you translate it first, then you again translate the translation. When we move to the practical example, I think the picture will be more clear. At this stage, you see a demodulator. It could be because it is an audio amplifier, you are only interested in the amplitude of the audio signal. So you get the information, you get the information out of the amplitude using a detector based. Your detector could be log periodic or DLVA type. There are many detectors available. We use from analog devices mainly for this application. So that was heterodyne receiver. Now there is another example of the receiver. This is also heterodyne receiver, but with the IQ implementation. We all in the communication systems. It was very. I was not good at learning digital communication or communication systems when I was studying in my bachelor's. Madam knows that she's my teacher. So, but later on, when I moved to practical aspects, I studied the systems, I implemented that. I learned a lot of what actually I have learned in the course, and how actually practically what is the significance of that, what you have learned in your BS or in your books and your lectures, in your slides. So that receiver is actually also a heterodyne architecture where you have a first mixing stage. The first phenomenon is the same, it just translates the frequencies. Then you have two mixers, 90-degree apart. That configuration known as a Hartley mixer. So that is the hardware part implementation in modern receivers. Some of the arrangements we make, you may also find this implemented on the digital side, because it can easily be implemented on the digital side as well. The purpose of this is to image reject, because when you mix two signals by 90-degree apart in phase on the same frequency, so you may reject the image produced for the signal. The significance of that is because in measurements, when you mix two cosines with the 90-degree phase, you get at an oscilloscope. You won't see that on spectrum. On an oscilloscope, you will find one signal in phase and another 100 out of phase. So if you try to sample that on a single port of SMA port out of the receiver, you would cancel out at some point. Your information will be lost. So to reject the image more effectively, this configuration is also used. This configuration sometimes you may find in implemented at hardware level, and many times you will find that the receiver heterodyne receiver architecture is implemented at this side which is implemented at hardware, and the rest is implemented in the software. That is known as hardware mixing topology. So it is easy to implement that in digital form. Now, I discussed first three types. First was homodyne, where you have a frequency translation near zero. Then you have a heterodyne, where you have a frequency translation a bit far from zero, from DC, but not too far, so that you have available Q factor filters. Then super heterodyne, we discussed two mixing stages. Now with the advent of time, there is another topology coming up, and it's very famous nowadays in defense industry, especially direct sampling receivers. With I recently read that by 2015, the sampling speeds of ADC or the tunneling speeds of ADC was around 1 to 1.5 gigabits per second. By 2018, the sampling speed is now around 6.2 gigabits per second. So with the sampling speeds increasing and the ADC is improving, so you have this topology coming up, where the incoming signal, any incoming signal, you just filter it out in your band of interest, amplify it, LNA. This is a harmonic reject filter. Since this is an amplifier, it will have an harmonic. If it is amplifying for 1 gigahertz, there will be a it's for a fundamental first harmonic at 2 gigahertz. To reject that this filter is implemented, then you have an ADC, RF ADC at this point. What is ADC does is it can directly sample any signal, any frequency. Previously, it was not any frequency, but recently at RWR, luckily we have a signal system implemented that can directly sample from 2 to 18 gigahertz frequencies. What actually in the theory we have read that for sampling frequencies, you need to have at least twice the available the frequency you need, the bandwidth you need to sample, or the frequency you need to sample, you need to have the twice the frequency of the sampling ADC to actually acquire information from that. But there is another concept of undersampling as well in the literature, and people have implemented that. And I won't go into the details because that is another. There's a lot of description involved to this direct sampling receiver. But this is an emerging technology, and what actually you do is you undersample the signal. And since as you must have noticed, you must have studied, when you undersample a simple signal, it lies into its own. The carrier folds back into the ADC bandwidth. So what happens is in these types of ADCs, you have an FS frequency. You undersample the signal, for example, your sampling frequency is 2 giga and you are sampling a 14 gigahertz signal. So 14 gigahertz signal will fold back into your ADC bandwidth. So there is a mathematical relations with which you can actually fetch back your information of the carrier between that folds. So actually, one of the simple systems currently it has been demonstrated as an RWR. It is an all digital receiver. What it does is it directly samples 2 to 18 gigahertz bandwidth, and then at the DSP level, digital level, the Nyquist folds. After every FS by 2, there's a Nyquist fold. So the original signal gets folded into different Nyquist folds. Using mathematical relations, you can actually fetch back the information from those Nyquist folds in the digital domain. The benefit of that system, it's small. It's because it has limited hardware involved, so you don't have many things to fail when you are working with that, when you are implementing it, when you are installing it on maybe some defense platform or anywhere. You don't have many things to lose. Everything is implemented in digital domain. So it's an upcoming thing that is on the rise. There's another many of you people working in the communication domain, you must have heard what they call is radar, JRC, joint radar and communication. That actually also is related to this, where you have an all digital receiver and it is doing a lot of things using a smaller front end. Previously, with the advent of USRPs and the RF data boards, the frequency was only limited to maybe 6 gigahertz or 7 gigahertz. But now the concept is changing. RWR luckily did send some of the engineers from our embedded departments to have the training on this. So they came back and they implemented their own hardware. So that we do have a system in RWR as well that actually samples from 2 to 16 gigahertz directly. So there's a lot of other things involved in the chip. The SoC, the RF SoC that we're using, I think it's cost around $50,000 to $60,000. So we have 2 of them. We are now in the prototyping phase. So that is another cost. But with the advent of technologies and the advent of the emerging new TSMCs, new foundries, so this cost will reduce. But I think this is the future that we should be looking at as an engineers or as a researchers. This is it fixing it?
The question only says what it should have required to use, but can you please elaborate your question?
Yeah, I just want to ask that, you're directly sampling the signal. So you must have required a lot of, GPU for the processing, as you said earlier as well.
In this case, usually you undersample the signal and you fetch them back in your Nyquist folds. As been studied in the literature that in our courses as well, after every FS by 2, there's a folding of the sampling frequency. So your first fold is FS by 2, then your second fold is 3 FS by 2, then 5 FS by 2. So between those foldings, your signal gets folded back, even you are undersampling that signal. So there's a small mathematical equations with which you can actually fetch the signal back from these folds. I cannot state at present that how actually data, if you are intercepting a data signal that has any modulation schemes, maybe FSK or ASK, QAM, PSK, how actually that would be affected. But in case of RWR, radar warning receivers, where you are only interested in the envelope of the signal, that actually is correctly and precisely that information is extracted from the received signal.
Okay. Oh, so I have another question. Can you state the values of ADCs? How much samples? How much was the rate of ADC which you used in your specifically in your design?
I think for this, I cannot state explicitly, but I remember I think 4 gigasamples per second. This one for direct sampling. For the other applications, I think generally we have 1300 MSPS, 1600 MSPS based on which application. We make a lot of systems, so those are different applications.
Okay. Oh, thank you.
Sorry, how do you deal with sidebands in case of super heterodyne receivers? Like when you are out converting a signal and there are two mixing stages. From the first stage would be 2 sidebands, then from the next it would make like 4 sidebands. How do you deal with it?
Well, in a super heterodyne architecture, as we move forward, I will share the practical example as well. The first, usually in most of the cases, only one of the LO is tunable. The other one is fixed. The first one, the tunable LO, usually is used for actually producing the 2 side bands. Then you have a actually band stop filter where that actually rejects the image. In this particular configuration, as we move towards the next session, I will share. It is in a high side, as I have explained earlier. It is a high side injection mechanism where you have actually your LO is on the high frequency bands than your RF frequencies. In that case, the actual mixing products can be rejected if you have precisely placed the frequency responses, frequency planning. I will when you move towards the software part, I will explain how actually we do frequency planning before implementing a receiver. That is actually a crucial part.
Okay, another question. How do we get output till 16 gigahertz if we are using ADC that can extract it?
That's the magic actually. When we study ADC, we have a concept of Nyquist frequencies. Like you should have at least twice the sampling frequency of the signal you want to actually sample. But as you, if there is another topology or configuration that is known as undersampling. When you undersample a signal, the signal gets folded into the Nyquist zone, in the first Nyquist zone. The first Nyquist zone is actually from maybe you can say 0 to FS by 2. Then the second Nyquist zone, FS by 2 to 3 FS by 2. Then to till 5 FS by 2. Then these are known as the Nyquist zones. So the higher the frequency you want to sample, the more it will be folded back into the Nyquist zones. So there are mathematics. I'm not stated because this is another interesting big area of interest. So where you can fetch the information. So there are the different mathematical relations which you can implement it at the DSP level in the digital domain, and then you can fetch back the incoming intercepts or incoming targets or incoming signals you are interested in. So it can be done. It has been practically implemented by 4 or 5 years when I started learning this. I was also intrigued that we were taught a different lesson. So, but it is done. It is being practically flown by different military aircrafts as well. So we learned it from the Italians. There's an Italian author who has written book on this. So that is just the theory part. When you come onto the implementation part, there are special ADCs, there are special amplifiers that we have procured for this special application to actually set up that hardware. RWR welcomes fresh minds, good minds. You can visit there, actually see that hardware working. It's also a good piece of technology under development there.
Can you please mention the name of the book?
I may share later. I have, but I don't remember the name. The author is Nori something.
You stated that the filters will be implemented in receiver. How will we get sharp transitions and frequencies will mix? How shall we separate that gradient?
For example, if you are asking about direct sampling receiver, digital receivers can implement, you can implement sharp roll-offs. In tactical receiver implementation, you have issues. Like in super heterodyne receiver, in the previous slides I have explained, especially in heterodyne architecture where you have a single mixer. So there is a problem when you actually move more towards DC. You need high roll-off filters that are difficult to actually fabricate unless until you have a high order cavity filter. They do have better Q factors or dielectric resonator filters. So that is a trade-off, because if you are, for example, if you are working at 500 or 600 megahertz, so a filter of that side will be very big size. Before LNA filter, we normally have bands. There could be different configurations. As we move further, I will share two different types of configurations where you have a single channel input and divided into different bands. There's a special application for that. I will share that later. Now I think we move towards the second aspect. the different aspects, different discuss configurations of the receiver, homodyne architecture, heterodyne, super heterodyne, all digital receiver. I have not mentioned there is another system as well, DLVA, digital log variable, where you actually only interested in the envelope of the signal. That is actually in the same topology that we use for have previously used for AM radios. You are only interested in the amplitude. So that there is another type of receiver as well. All those receiver design trade-offs, come at complexity, of course, how much actually the effort you want to put, how much components you want to procure, how much design or fabrication or manufacturability you want to acquire. That's come across complexity. Then, of course, the cost. All digital receivers might seem very intriguing and might seem very efficient, but the RF SoCs and the ADCs related to that are pretty expensive, and your frequency of interest might be lower. So there could be other suitable solutions for that purpose as well. Then, is there any frequency modulation, or you are only interested in the amplitude frequency? So that is also an important aspect, which receiver design actually would fit in which application. Then particularly the antenna type. If you have a receiver, you need a high low noise performance. So antenna type usually we ignore, but antenna type also plays a big role in that as well. You need a directive antenna, you need a low noise antenna, you need a LNB antenna for the satellite reception. So antenna type also plays a role in your receiver design architecture as well. Then the receiver range and the direction. You have a duplexer mode, or you have a single channel communication. So these all actually the design trade-offs when we are selecting a configuration for the receiver. So they do come close and play a role in our selection. Now, the previous part was more of the literature review that since I am also a student of these technologies and be working on them, so I've studied on them. But when a designer, when a customer comes to you, he brings you a task. So you need to look into this. What aspects you need to think about it? What questions or the information you need to ask the customer? What actually he is wanting from you as a product. So from now on, we will mostly discuss and focus on that aspect. So what parameters we look into while actually designing a picture of the design before implementation. Later on, we will go to the implementation side as well. So the first, when a customer comes to you, and we are considering the super heterodyne receiver because most of the application it works, and it is the most abundant form of the receiver where you have two mixes and frequency topology. So first thing I may ask is the frequency plan. What actually is the intended frequency, input RF frequency he is interested in? Then I will be thinking of frequency translations. Since you have two mixers, you need to frequency translate between bands. Then you have a tuning LO ranges, tuning local oscillator. As in heterodyne, you have two mixers. So you have one, in a simple configuration, you have one tuning and the other one fixed. So you need to look into what would be the tuning LO range, the range of the tuning LO, and what will be the range of fixed LO. As we move further, I will explain you how actually frequency planning is done before implementing a receiver. So that is the first thought. Any customer comes and brings in this problem on the table, I will just thinking on the frequency plan that need to be implemented. Then another important aspect of any receiver is selectivity. He might be interested in telling you his input frequency, but there will be an complete RF bandwidth, then there will be an instantaneous bandwidth. We will come to that later, what is the difference between the both. Then, as I if your receiver at a lower frequency bands from 100 to 1 giga, then you might have to think about filters availability, the roll-offs. If there are adjacent bands are too close, you need very sharp roll of filters. Okay, the microstrip filters won't work there. You have to accommodate the cavity filters there, resonant cavity, iris-based filters. If those filters are used, then the size will increase. So if I don't use those filters, I use the PCB mount based microstrip filters or LC filters, then what will be the trade-offs? How I will manage the band overlappings. So that is also comes under the umbrella of selectivity. Then there is another gain equality, dynamic range. We believe in equality, but the gain equality actually is based on since you are looking into 1 to 1000 megahertz of bandwidth, or there's a receiver I will show later 1 to 18 gigahertz bandwidth. It's a big bandwidth. You need an equalized gain at the ADC. You don't want your ADC to actually at one time it is sampling 1 volt, at another it is sampling 0.2 volts. So that also actually jumbles up the information in the amplitude. When you are working with when you are more interested in the information in the amplitude of a signal, so you need a equalized gain. So in practical receivers as well, you will see markings on the receiver data sheets like plus minus 2 dB, plus minus 0.5 dB, plus minus 1 dB. So greater the bandwidth, more tolerance you will have to pay for the gain equality or gain equalization. So in practical, we have different available models from mini circuits, analog devices, other companies that actually equalize gain. These devices are known as gain equalizers for broader bandwidths. What actually they do is actually a filter. They may fall from one side and rise from other side. To actually, depending upon your application, your receiver design, you can have gain equalization is a very important thing in DLV is where you are actually getting the information out of video signals. So you need an equalized gain response at the ADCs. Then there's dynamic range. Dynamic range, we will discuss that later as well. Dynamic range is actually the minimum and the maximum level of the signal that your receiver can accommodate. The minimum level will be at its noise floor, sensitivity, we will discuss that later as well. And the maximum will be until it saturates. As they are amplified, there are passive circuits, everyone will have its 1 dB compression points. Then the other thing after selectivity frequency plan, I will ask them their sensitivity. What actually is how much sensitive receiver we are talking, and since we are relaying information, and every frequency spectrum has its own noise sources. So in the RF spectrum, we have a lot of, since there's a lot of easy communication. If you are working in 100 to 1 giga, there are a lot of radiating sources. There is GSM, there is TV, VHF, UHF. Then there is HF radio, then there is VHF radio, then there is open ISM band for 33 megahertz, then there is RC circuits. There are a lot of frequencies in the environment. So that is the noise from the outside sources. Then there's another ambient noise of your receiver that is due to electronic motions. We study a lot in our basic courses. This is due to the vibrations of electrons. So that contributes the noise figure, more onto that later. Then other thing is the receiver gain. Receiver gain is, for example, if you are receiving a signal at minus 70 dBm, then how much gain in the first step you need, for example, 48 dB gain to get the ADC sample. Usually the ADCs have a noise floor for good to best ADCs, you will see they will have a noise floor of around 60 to 65 dB. I am quoting 65 as upper margin, but usually 60 dB, minus 60, they cannot go beyond minus 60 dBm. So what you need to do is you need to have, and your noise floor of a receiver is around minus 80 dB. So there's a gap of 30 dB between them. So you need to have at least minimum 30 or 35 dB gain to bring that signal up. So it is to sample and the digital domain to be displayed or the information to be extracted. So receiver gain, you have to plan that accordingly. Then there is phase noise. Phase noise, I will have a practical measurement slide on that as well. Phase noise is actually, we know PLL's phase lock loops. We know PFD's frequency phase detector. What actually happens is frequency phase detector, and you have we have clock sources, PCXOs, OCXOs, temperature compensated or oven crystal oscillators. So with those clocks, when we drive a PFD's frequency phase detectors, naturally there is some murmuring or jittering noise over the clock sources. These clock sources actually contribute toward the phase noise. Now, what is the effect of phase noise? Phase noise in the spectrum or in the usual domain. When you input a signal into a spectrum from an oscilloscope, from a function generator, you get a single peak. But when you reduce the span of the signal, it becomes a skirt. So that skirt of the signal actually due to the phase noise, the spread of the signal. Now imagine if you are interested in a signal strength, you want to measure around 83 dBm, minus 83 dBm, minus 90 dBm signal, and your skirt is that much wide. So your LO will actually map the weak signals in in that skirt, and you won't be able to detect that. So phase noise in any receiver you see commercially or any vendor, there will be a parameter of phase noise. How much phase noise is, that is the measure of the fall of the skirt of the main LO or the receiver frequency out. That is actually contribute the sensitivity of the receiver. Then the next is the P1 dB compression point. It's a very famous term in our microwave circuits and systems, derived from usually amplifiers, where your system acts linearly. When you are increasing the input power, your output power increases. After some point, you will notice that as you're increasing the input power, the output power is not increasing that much. It may be increasing. You have increased 2 dB of input power, 2 dBm, then output power increases 1 dBm. That is actually 1 dB compression point, that your gain has compressed 1 dB. After that point, there is a 3 dB compression point, then there is a saturation. So you need to think of the system before that, a linear system before that 1 dB compression point, because the effect of 1 dB compression point is that after that 1 dB compression point, the harmonics increases. And when the harmonics increase, then you have two signals. You are feeding two signals to your system, and there will be mixing products, and you won't be able to resolve your IF or frequencies at a later stage. So that is the significance of P1 dB compression, but we will see that come to that later as well. Then there's another aspect, the most famous. We have already the SNR on the minimum detectable signal. SNR usually is a user-defined requirement. So user will also tell you he want to sample the signal at 3 dB SNR, 10 dB SNR, 20 dB SNR, based on which application the system is being implemented, or which what is the particular purpose of your hardware they are fetching from you. I'm talking about positive SNR, but there are negative SNRs as well. People do fetch signals from the GNSS people. They do have signals embedded inside, so they have processing gains. I think that then coding gains. They can fetch the signals below the SNR levels. So it all depends which application you are. You need to focus on that, which application you are designing or targeting the receiver for.
I have a question. You mentioned that if we have a more gain in equality gain, like we have gain, then we will have a broader bandwidth. So by this we can decrease the band overlapping, right? Is it so?
No. I can explain you good. But gain equalization is, for instance, on your ADC you have like in one of a system we are working on. We are more interested in the amplitude of the system. When the signal is received, we are more interested in the amplitude of the system. The frequency aspect we are not interested in. So when that signal, let's assume that its bandwidth is around 4 to 10 gigahertz. When this much bandwidth signal will be sampled by the ADC, you need a uniform envelope of the signal. You don't want upside down ripples or fallings into the signal, because you need your ADC won't be able to. Your ADC will, at one time it will be sampling 0.1 volts, 1.2 volts, 0.8 volts, 0.2. The actual signal onto the incident on your antenna might be of uniform amplitude. So that is the non-linearities or the discrepancies added to the signal by your receiver. So that concept or that I would say parameter is known as gain equalization or gain equality. What you do is, what you can do for this is, you have in spectrum analyzers, the modern spectrum analyzer, they have, and all receiver you will find digital DSS, digital step attenuators with maybe 0.5, 0.25 dB attenuation resolution, 1 dB resolution, 2 dB resolution, depending upon how much the equalization you want. That is one way. digital step attenuation to do that. Then the other method is, I have already shared that is gain equalizers. Gain equalizers actually are filters with attenuations. So what they have, maybe if your actual response is maybe this way falling, so the gain equalizer will be rising. So it will attenuate the first part, and then you will be have an equalized. Then equalization cannot be zero in real systems. It comes at maybe plus minus 1 dB, plus minus 0.25 dB, plus minus 3 dB. So the lower it is, the better it is. But there is a certain limit. The wider the bandwidth you are looking at, the more challenging it becomes to actually equalize the gain. So that is actually the theory of gain equalization. Then after sensitivity is fidelity of the receiver. What actually are you making? Does it has a capability of image rejections? It's filtering. Spurs are usually unwanted when your system or your receiver, then when the mixers are overdriven. Like you are expecting that you have designed a receiver for the maximum power of minus 20 dB. And if it is fed by minus 10 dB, 10 dB more, minus 10 dBm, 10 dB more power, then how it will behave? There will be spurs, the first mixer will be overdriven. So in one of application, we use limiter. Limiter actually limits the input power so that your system behaves in a linear manner. It doesn't turn into a non-linear mode. Then you have intermodulation, IMD effects. Intermodulation in communication systems, we have a formula of NF1 plus minus MF2. When you feed two frequencies to a mixer, one is from the LO, the other is from the RF source. So you have plus minus, you have a lot of mixing products. When those mixing products, when the mixer is driven into overdriven, so those mixing products themselves mix and they form IMDs. Then you have in the spectral domain, you see a lot of spurs. Basically, you have your intended signal of interest, and you have a lot of other spurs in between. These are known as intermodulation distortion. They cause distortion in the envelope, they cause distortion in the frequency domain. And if some of them falls in your band of interest, many of them in a super heterodyne architecture, due to filtering, many of them will be rejected because of frequency mixing. They may fall out of band. So, but if they come into your band, then it is a big problem. But in many of the receivers, you will see a spur level as well, DBC, minus 40 DBC, minus 50 DBC. The user, the customer may ask, okay, you cannot avoid, because as you move towards overdriven systems, or when you have high power systems, then you do have spurs. But what should be the level of them? So they will quote with, they should be minus 50 dB down, minus 60 dB down, minus 40 dB down. We will talk about that later as well. Then at the end, the frequency accuracy. Since in the super heterodyne architecture, you must think of like you are, for example, this band, this was 1 to 18. You are mixing that with 24 to 40 gigahertz. You mix those bands, those two bands, and you translate that on 22 gigahertz. Then 22 gigahertz, you mix again with 22.95 giga. Then you translate that into 950 megahertz. So with that much of translation, frequencies going, frequency spectrums going here and there, you need accuracy of the frequency. You need your input incident frequency was 10 gigahertz, and for example, it was 10.5. In a system I will say later, that 10.5 gigahertz should be translated to 950 megahertz at the IF stage. So you need an accuracy. Who defines the accuracy? The accuracy is defined by the PLLs. The fixed frequency, the fixed frequency FLO. I will share later on what type of fixed frequency sources we use, and the tuning frequency TLOs. TLOs, tuning local oscillators. What actually tuning local oscillators usually in one of application we are using DDS, but in my application, in one of my I'm working on, we are using this architecture. It produces around 24 to 40 gigahertz signal. So how accurately it can produce, it depends upon the accuracy of the clock, the PLL, the programming, it is either n-type PLL, integer type PLL, or fractional and PLL, how much accuracy you are getting out of that. So that is it comes in the fidelity, the frequency of accuracy of the system you are offering. So this was for my learning that I have gathered with the years, that okay, these things when we discuss with the customer, when we have a design approach, we should look into that things before finalizing any prototype or layout plan. Okay, so now we talk about the first. There are a lot of parameters, but I will define or discuss just a few of them before going into toward the design example. The most important of them. Any receiver, when you see, will be marketed by its one thing. That is the noise floor, the more sensitive signals it can detect, that will be a user trademark. Or you can also say, okay, this much low signal, because low power signal it can detect. The low power signal is usually limited by the noise floor of the system. The natural noise flow, you can filter out the unwanted signals in the ambient environment. I have already shared with you if you are working with within the band of 100 to 1 gigahertz frequency. So what will happen is there are a lot of other frequencies around in the ambient environment. I've shared with you TV signals, GSM signals, VHF radio signals, VHF walkie-talkie signals, VHF SDR signals, HF radio signals, MHA radio signals, then open 433 megahertz ISM band signals. So there's a lot of things going on in that environment. But as you get those signals into your receiver via your antenna, so the first thing they will see is the noise, the electronic noise contributed by your own receiver. That you cannot lower. That actually is driven by the temperature of the system. You move to higher temperatures, then your noise figure will degrade. If you have a proper cooling mechanism, then your noise figure will be stable. In the practical, all data sheets you will find with amplifiers, LNAs, zoners, amplifiers, there is a merit of noise figure. So in terms of making a sensitive receiver, you need to consider a lot of thoughts about noise figure. Like a practical example I can share you before going into the detail of this. When I joined RWR, there was a system previously. My senior who made that, he worked on that. He built a prototype of that. That it has a noise figure when run on first 5 to 10 minutes. It noise figure was below 7. But after maybe 30 minutes, 35, 40 minutes, its noise floor of complete bandwidth 1 to 18 gigahertz will be above 13 dB. So that was a huge difference, because during the design or prototyping process, he did consider the noise figure, but he didn't consider how we will remove the heat from the LNAs. So the whole assembly will actually, its temperature will rise with the DC current flowing. So you need to also plan, you need to think the mechanical aspect as well when you're designing a system, its DC contribution towards the degradation in temperature as well. So that's one of the example. Now for example, in the receiver noise floor example, you can see TE actually is a resulting noise temperature referred to the input. At the input, and T1, first component cascaded, second component cascaded, third component cascade. These are the temperature for that. You can have there's a simple formula for to calculate noise temperature from the noise figure. And what you can do is you can either do calculation on both way, but nowadays there are a lot of tools available on MATLAB, Arc System View, Genesis. They can directly you can just put the values of the models of the amplifiers, their noise figures, tentative noise figures at maybe 25 degrees centigrade or 40 degrees centigrade, and they will contribute your noise flow or noise figure. So as you can see, the important thing to note in that relation is that after the first one, if the first component T1, you can see the first component T1, its temperature or its noise figure will be directly contributed towards the whole system cascaded system noise figure. So whatever you have, any passive component you put at the front of your chain, at the beginning of the chain, it will contribute towards, it will directly be added. Then the second component, for example, the first component, we assume that it is a cable between the antenna and the system placed in a cupboard, in a rack downstairs. So its loss actually will be directly contribute towards the noise figure. It can be added as a whole. For example, the loss is 1.2, 1.5, or 2 dB. You can directly add that into the noise figure. Then the second component, for example, it is an LNA. We assume it is an LNA. If it is an LNA, then it has a gain, and you can say if its noise figure is 1.3 dB, then you can divide it by its gain. The gain will be usually higher, maybe 20 dB. So it will have a lesser contribution. So as you move down the chain, more and more components will add up, and more and more components add up. There will be lesser effect on the noise figure. In the simulated results later on, I will also share with you that how actually it reflects. So this is from the noise figure, and during the selection process, you have to actually think of it. Which component will contribute to more noise, and which component to place first, and which component to place at a lower stage down the chain. Now, there's another parameter that is known as noise factor. Noise factor is usually the ratio of SNR to input, SNR to output. Noise factor is, I think, it's a linear. You take a log of that, that becomes a noise figure. So, as an RF engineers, and I think most of the people, they do already know that. Now, any system, any architecture or any receiver you are making, you will be offering the customer or the end user, he will be asking you the available bandwidth, the bandwidth you need to offer does contributes directly to the noise figure of the receiver. The generic, the famous formula KTV, you have noise power equals Boltzmann constant, the temperature, the system temperature, and the bandwidth. The system temperature, usually if it is a reference, maybe you can, in general calculations, we usually have 315 Kelvin. It's a good assumption. And then you have a bandwidth. So for one, there's a standard that for 1 hertz of bandwidth, the noise floor is around minus 174 dBm. Then you just convert your bandwidth. For example, it is 500 megahertz, 100 megahertz into log scale, then add it to minus 174. That will actually become your noise floor of the system. So that is a quick way to estimate noise power per bandwidth. The wider the bandwidth of a system, the more noise it will be picking. The more noise sensitive it will become. So previously we have talked about different architectures. If it is an all digital receiver where you have 4 gigahertz bandwidth or 10 gigahertz bandwidth, compared to a system that has 500 megahertz bandwidth. So of course, 500 megahertz bandwidth will have a lower noise floor. It can catch weaker signals compared to that. So these are the trade-offs for different systems. Then before moving toward the final session, let's see this plot. The different terminologies we have discussed previously in the design parameters, you can see. For example, we have a simulation settings of 500 megahertz bandwidth, and the input frequency is 6 gigahertz. The first mixer IP3, I'm not going to IP3 at present, plus 17 dBm. Let's ignore it at present. You can see that red and blue. Red line constitutes the fundamental or the. You can see this line. This is the input signal, and you have input power ranging from minus 80, minus 70, minus 60 dBm as increasing. Then output power is increasing because in the receiver you have some gain. You have incorporated amplifiers. So the input signal, it gets translated to some one frequency to another due to the configuration of the receiver. But actually, what happens is as you increase the input power, the output power increases. For the fundamental, the IP3 is intermodulation distortion. of the third order, like I already shared with you that you have MF1 plus minus NF2. So that is the general relation we use to compute the first and third order harmonics. So you have 2F1 plus F1 or 2F2. These are the third order harmonics. I've not stated there, but it's a theory thing. So you see this point, the purple color line, this is actually the noise floor of the system. You cannot see below that noise floor. So at this point, you can see the signals comes out. You are increasing the power. Maybe not on the screen. You are increasing the power, and from minus 90 at this point it's minus 80, then minus 70. Around minus 80, the signals comes out of the noise floor. You are increasing the power, the signals comes out of the noise floor, and it is increasing. At this point, this is around the compression point. You can see the minus from minus 20 to minus from minus at this point you can see this is the 1 dB compression point around minus 20. After minus 20, your gain is starting to fall. It's not increasing as much as the input was increasing. So that is the point, that is compression point. Your gain is actually starting to compress. So at this point, you can also notice that the IMDs also are increasing. You can see this behavior, this is also increasing, and after that point, the gap is actually closing in. So that is actually the linear, before that point is your linear behavior of the system. You don't want your receiver to go into that mode, because a lot of information will be lost, and the spurs or the intermodulation distortion will increase as much that the original signal might be swallowed by them, and you won't be able to get valuable information. So that is for IMDs. Now another parameter you can see is at the back is SFDR. That is spurs free dynamic range. I have already shared with you the concept of spurs, how actually spurs are actually unwanted signals that comes because of the non-linearity of the mixers. Because mixers are non-linear devices based on diodes, and they are among the most important components that we cannot replace in superheterodyne architectures. So they contribute towards spurs. What actually spurs does is they may come into your in-band. For example, you are interested at an IF frequency of 700 to 1200 megahertz, and your spur may be fall in band, maybe it may fall at 800 megahertz and come out of the noise floor. So you won't be able to remove that. So spur free dynamic range or instantaneous spur free dynamic range, they are calculated based on how much margin you have before the spurs arise. So you can see that the noise floor is 44 dB and the maximum signal is 80 dB. So around 48 dB instantaneous dynamic range, and the receiver gain is 38 dB. I have already shared with you the basic significance of your receiver gain. You should have as much as gain for the total chain, so that your signal should be high enough for ADC to sample. Usual ADCs, I'm repeating again, usually have around, if it is a good of ADCs, it is ADC of the noise floor of the receiver will be around 60 dB, minus 60 dBm. It cannot see below that. Now, if you want to detect a signal maybe of minus 80 dBm power, minus 80 dBm or minus 70 dBm power, you need to increase that to come into the range of the ADC. So that is actually the significance of this plot. Now, I think we will move towards a break, and if anyone have a question from the far side, so we will accommodate that.
ये सकती है कि जो चॉइस है तो
Welcome back, everyone. Review now. Thank you so much for your kind patience.
ये आपको बंद करना पड़ेगा लास्ट टाइम वाला मसला है। मैंने स्टॉप किया ना, अब आप स्टॉप कर दें। Assalamualaikum. Welcome back. And हमने लास्ट सेशन में डिस्कस किया टाइप्स ऑफ रिसीवर्स। उसमें होमोडाइन रिसीवर हमने देखा, हमने हेटेरोडाइन रिसीवर देखा, हमने सुपर हेटेरोडाइन रिसीवर देखा, उनके बेसिक टोपोलॉजीज देखी। फिर हमने डायरेक्ट सैम्पलिंग रिसीवर देखा, हमने इनका डिफरेंट का कंपैरिजन किया कि which one is better than the other for our applications। उसके बाद हमने डिफरेंट एस्पेक्ट देखे, डिजाइन एस्पेक्ट, फ्रीक्वेंसी प्लान। जब आप एक प्रैक्टिकल अप्रोच से चल रहे हैं, फ्रीक्वेंसी प्लान क्या होना चाहिए, आपके पास सिलेक्टिविटी, व्हाट इज सिलेक्टिविटी, देन व्हाट इज सेंसिटिविटी, देन व्हाट इज स्टेबिलिटी। कि आपके पास एक यू हैव अ कस्टमर, देयर इज अ सॉल्यूशन ऑन द टेबल। सो आप क्या कर सकते हैं कि आप ये चीजें इन माइंड रख के उसे डिस्कशन कर सकते हैं। Then we move towards few of the parameters I needed to discuss before going to the detail. The receiver noise floor, how it is computed, how it is affected by the selection of the components in the chain. Then the noise factor, where it is a linear ratio of SNR at the input and SNR at the output of the receiver. Then the usual calculation of KTB of any receiver you have. The wider the bandwidth, the higher will be noise power. Then at a given temperature, you can compute the bandwidth. The usual mark is around minus 174 dBm power is per hertz. So any bandwidth, the rule of thumb is any bandwidth you have, you can take a log of that and add it into minus 174. Then you will get the noise floor of the system. Then we discussed about amplifier parts and its significant, the fundamental IMDs, the noise floor. We talked about that. Now, before going into the actual design, the last parameter I need to discuss and share is the phase noise and its effect. of the receiver. You can see that is what I was talking about. This is actually, for example, the LO frequency, the tuning LO frequency or the fixed LO frequency. You can see this is the exact frequency. You can see this is the point of the frequency point. For example, this is the tuning LO. So let's assume its frequency is around at the runtime, it is around 20. It's around 23.7 goes bit bigger. 23.75 gigahertz, for instance. We will use that frequency on the later on. So I have added this numeric figure to that. So as you can see, in theory or in our simulations, we have a single peak around this value. But in practically, you have a skirt of frequencies going on. So what happens is phase noise is the measure of this spread. The skirt actually that is becoming. What the drawback of this parameter is, if phase noise is you have a greater phase noise in comparison to another receiver, you won't be able to, for example, you want to detect a weak signal at this point. So it will be mapped inside your receiver phase noise. You won't be able to detect that, even if you have a better noise flow. So phase noise contributes a lot towards the efficiency of the receiver. For instance, you are working in GSM bands. Your cell phones have a very good phase noise. They have a sensitivity of around 110, minus 112 dBm signal they can detect in picowatts. So they have very good and very efficient phase noise. So they could detect very minute channel spacing because the channels are the communication channels are spaced maybe 1 mega or 2 mega spacing of guard bands. So you need to distinguish between them. So you need a very good phase noise. You need a very good local LO, local oscillator, tuning oscillator to detect the frequencies. So who actually contributes to the phase noise? The phase noise is the PFDs of PLLs. The frequency phase detectors in the PLLs. As in the architecture of PLLs, you know that you have a feedback signal coming back. You have a reference TCXO or OCXO, temperature compensated oscillator or oven control oscillator. So they actually, when they are mixed up at the PFD, frequency phase detector, they contribute toward the phase noise of the receiver. Then there is clock signal discrepancies from the crystal. So the better the crystal you use, the lower the phase noise you may have. You may use atomic clocks. Now they're readily available CSEC models, cesium and francium models. At RWR, we are using as a test bed for test clock setup at the ground node. Yeah, I think using a cesium clock, cesium atomic clock. They have an efficient phase noise with very little clock drifting. So we do use them there. So they would, that is a problem of phase noise. And then now I will share a practical example of measured phase noise. Second. You can see this is a measured phase noise. Most of the spectrum analyzers, they do have a separate function where they can actually measure the phase noise of the receiver of any LO. For example, you have a tuning LO of around 23.75 gigahertz and a fixed LO of 22.95 gigahertz. You can switch the spectrum analyzer to phase noise measurement mode. The more calibrated the spectrum is, the more accurate with it. By the way, this picture is from the spectrum analyzer at 26 gigahertz we have at RWR. Not that much calibrated, but this gives an idea. You can see in this section, you can see that there is a carrier. Then you offset from that 100 hertz, then 1 kilohertz, then 10 kilohertz, 100 kilohertz, and 1 megahertz. These deviations are standard. You will see any local oscillator, any PLDRO, any dielectric or resonator oscillator, any gun diode oscillator. You will find phase noise power of the carrier at these offsets. This is a standard 100 hertz and 1 kilohertz and 10, 100 and 1 mega. So you can see as you move away from the carrier, the skirt falls. So you can see the first power at 100 hertz is around minus 81 dBc, then minus 79, then 101, 10, 115, 128. What I can share with you that the rubidium or cesium clocks, they do have at 100 hertz, they have around minus 101, 102, and at 1 kilohertz they may go to around minus 123, minus 1. The best 150 dBc. They're very good at that. So in comparison to this one is you can see the frequency is around 2.238 gigahertz. It's quoted with the carrier frequency. It's 2.238. So you can see minus 81. Minus 81 is a good metric, but you can see if you want to improve this, you can have a better reference clock, more expensive one, either the TCXO or maybe the atomic clock. You can replace that to lock your PLL, or there is if it is a fixed LO, then rather than using a PLL, you can use a PLDRO. PLDRO is a dielectric resonator, phase locked dielectric resonator oscillators. They have very good frequency stability and efficient phase noise. They can we usually order them from a Chinese vendor, and they are around plus 13 to 14 dBm output power, enough to drive a level 13 or level 10 mixer. So we use them, and PLDR is a good option for the better phase noise performance. Now we move towards the final session and final an important part of this session that I needed to share with you, that hands-on experience that I have in designing receivers. So this is a super heterodyne receiver architecture, a complex one. This is for a special application, and you can see the input is 1 to 18 gigahertz. The architecture is super heterodyne. The 1 to 18 gigahertz bands are divided into octave bands. By octave bands, I mean that the first one is 1 to 2 giga. The first one is 1 to 2 giga. Then there is 2 to 4, then 4 to 8, then 8 to 12, then 12 to 18. The purpose of dividing them into octave bands is that every signal you receive, for example, every signal you have a complete octave band. If any spurs arise, if any carrier arrives at 1 giga, its harmonic will fall at 2 giga at the band edges. So you can regulate between band edges. So dividing between octave bands, you can have a good noise figure configuration. We'll come to that later as well, how this helps. So in this configuration, we borrowed that design originally from a Western design architecture, and we produce better results with our design scheme. You have dedicated antennas for that. You have band pass filters in the beginning. These are the strip line band pass filters. Then you have built-in test couplers. These couplers are directional couplers. There are two purposes for this coupler. One is you can inject test signals. For example, this receiver may be above an aircraft or a tower or a remote site. You need to test that. So built-in test couplers, you should actually have in any receiver or any model you are making. So you can have a built-in test signal for this application. You can get the signal from this part to test the receiver gain parameters, noise figure, noise floor, inputting a known signal. In addition to that, what you can actually use built-in test signal for RSS estimation. For example, in this receiver, you can have a switching circuit at this point, and you can from one path you inject a test signal, and the other path you may sense the received signal strength. Then according to received signal strength, you can adjust the, for example, if you are in your environment, you have a signal of around minus 60 dBm, and your receiver saturation is minus 40. So you need to plan accordingly. If the signal power is rising, so at this point you can have a decision of receive signal RSSI indication, and your DSP board or FPGA that is controlling every module, it will work. So before going into more details, I will introduce you towards the different sub-modules of the system. This is the first signal amplification unit that contributes a lot for the RF amplification and noise figure. Then this is the switch matrix. A ladder of matrix is used for switches to actually achieve better isolation. The switch matrix actually provides isolation between bands of around minus 100 dBm, 100 dBc isolation between bands. Then from there on, you can see this is the first BSU amplification unit. This one. Then this one is the frequency upconversion unit. The 1 to 18 gigahertz frequency bands you receive, you upconvert them to 22 gigahertz. You can see there it is 22 gigahertz. 1 to 18 gigahertz is mixed with an LO ranging from 23 to 40 gigahertz. That LO is provided by this part, this LO part. This produces the 23 to 40 gigahertz signal, and that is the upconversion mixer. The market mixer, very good mixer, very good and reliable performance for Bayer. Then at this point, you generate, this is first IF1. First IF. The first IF of the system is centered at 22 gigahertz and around has a bandwidth of around 1 gigahertz. Then you have this second mixer. We call it down conversion block. You have a PLD arrow. This is a PLD arrow. From the PLD arrow, you drive the mixer. Since we are using passive mixers, you drive the mixer and you convert the 22 gigahertz to 950 megahertz. 950 is the center frequency, but now due to these filters, these filtering IF filtering stages, the IF filters, they limit the bandwidth to further 500 megahertz. At present, this system is at 500 megahertz, but in the next stage, it will be converted to 1 giga bandwidth. So 1 to 18 gigahertz, for example, we'll make a spectrum plot here. So this is 1 to 18 giga. Just to give you an idea of how I did the frequency planning. For example, this is 1 to 18 giga. Then 1 to 18 giga is mixed with, the drawing is not that great, but bear with me. It is mixed with around 23 to 40 giga. Now mixing these two frequencies, the tuning LO is a tunable LO. It is controlled, it is a PLL controlled digitally by the FPGA. The FPGA controls that. So it transforms both the frequencies to this band in between. There is a 3 giga or around 1 giga, I think 1 giga guard band here. So it centers the whole spectrum at 22 giga. So you can see that is the frequency planning for this. 1 to 18 is mixed with 23 to 40, and that folds up at 22 giga frequency. Now that's a signal bandwidth at this point is around 1 giga. The problem why we used 1 giga filter and later we converted that into 500 mega, I will share shortly with you.
Sir,
Gigi,
in between, I would like to take questions.
just let me finish this diagram then. So that was the frequency planning at this stage, 22 giga. Now all the spectrum that you are receiving is centered at 22 giga. Let's assume this is 22 giga. Now it's centered at 22 giga. Then we have a PLD arrow here. The PLD arrow's frequency is around 22.95 giga. What is close to that is the single frequency, 22 giga. Again, high side injection, it is 22.95. 22.95. So what happens is when you mix them, F1 minus F2, F1 plus F2, we reject the upper side band, and the 950 is centered around this. This is 950. It comes around 700 to 1200. This is now my IF. So here you can see this is this mixer when mixed with this frequency range, and this, and at output you get 700 to 1200 megahertz bandwidth, and that is how the frequency planning of this receiver is being done. It is a very reliable. We have checked it for spurs or levels around minus 90, minus 80 dBm power. It's very clean and very efficient design. We have tested it, and I will share the results later and get in the detailed discussion of different modules. The whole of all the modules at different stages are being controlled by a central controlled FPGA. It monitors the DA states. You can see there is a lot of these are actually digital step attenuators, different positions, strategic location. We have simulated them, we have tested them. This is also DSAs. So these are also DSAs. So we do control them based on which frequency band you need, because there are a lot of amplification, involved. Different types of amplifiers. Each amplifier has its own gain variation. Maybe at 1 giga, its gain is different, and 10 giga, its gain is different. Maybe a margin of 3-4 dB or 1 dB. So a lot of selection and a lot of troubleshooting done on this chain before finalizing. So before moving forward, any questions of you? So I will welcome them.
So we have a question. Which software is used to plot the block diagram?
Visio. The block diagram is made on Visio, and for another aspect.
Are there any analysis tool for the frequency planning?
Yes, I will share that. Before going to the detail, just to mention, because now we're moving forward. So this in this whole design, actually, what actually to take home is that the first two stages when you are planning to design a frequency planning can be your own. You might be interested in N1, L2, GNSS, lower frequency bands, but the first two stages, they are the most contributed towards noise figure. The lower you want to see into the noise floor, the more precautions you want to take in this section. Before that, this is the first mixer. Before the first mixer, what component you select, how much noise figure they have, how much gain slopes they have. It's all provided into the data sheets. You need to view them closely, then get into the simulation modeling. So the first two stages, mainly we are concerned about the passive component. For example, there is a filter in the beginning. We can't remove it because it is a mandatory part of the antenna to actually band limit the system. In this special 1 to 18 gigahertz receiver, we are using special antennas for this as well, for CEX and KU bands, because those antennas are made up of waveguides. So waveguide usually antennas have better noise performance as well, because antennas are usually broadband systems, but when you have a cavity at the back, like a waveguide has native waveguide, so they will limit the band. They will naturally act as high pass filters, so they do perform, give you a better noise figure performance as well. So in this part, we take care of mostly of the noise figure. You should not deteriorate in this part, and the IF chain mostly. This path, we usually are interested in we usually have gain amplification. Major gain amplification we do at the IF part. In the simulation results, you also notice that the first two stages, the first few stages, they contribute towards the noise figure, and the last stages or the IF stages, they contribute towards the gain. So gain and IF, gain and noise filter, we have to settle between them in this. Now in this 1 to 18 gigahertz receiver, there were a lot of voltage rails, some amplifiers running at 3 volts, 12 volts, 10 volts. So for this VCO tuning voltage was around 25 volts. So for this configuration, we have to accommodate a special power supply as well in the receiver design. But in the next generation, now I'm working on, we have actually find a way out. We will exclude the power supply, reduce the FPGA size using an FPGA cutout board. This was a bigger board because initially there was a lot of control connections for DAs. You might be questioning what is this part? Going at the end, this is a switch. These are also filters, three inline filters. This is actually, as I already told you, already shared with you, KTB, the narrower bandwidth you are looking at, the more weaker signal you can track and sense. So this part what actually does is you have a filter bank, switchable filter bank. Switchable filter banks, what it does is you have a 500 megahertz straight path, then you have a 250 megahertz, 100 megahertz, 20 megahertz. You can lock at any frequency. Go to a smaller bandwidth, go to a smaller KTB, and look down down further into the noise floor. So that is the application. This hardware has been fabricated, tested. It's in field trials. Now we will move towards the software part. How actually we implemented that into our software. Before going to the software, I will share with you the frequency planning. I have previously shared with you the frequency plan, that how 1 to 18 gigahertz signal were mixed with 23 to 40 gigahertz signal, and in between them there is a band we mapped at 22 gigahertz. I will share with you on software as well. For example, this is the plot from system. Similar configurations are also available in MATLAB and Genesis as well. And it's up to you. So you can see this yellow mark is the actual 500 megahertz bandwidth, where you are. This yellow part is actually the 500 megahertz bandwidth you are actually you want to see. And these are the spurs, as I told you. It is NF1 plus, you read that in communication systems. Any mixer, when you have two inputs, F1 and F2, though N and M are integer values, so you have a lot of products coming out of the mixer. So you need to frequency plan as such that you don't have any spurs where you are actually playing going to play your IF, where you get your first IF. The second IF is just for translation, frequency translation, because you are up converting. In my case, we were up converting to 22 gigahertz. The second IF was just to shift that whole band to frequency where it will be able to, we will be better able to, our ADC will be better able to handle that. So that was it. Now we move toward the software experience, what actually is there. For that, if you have any question.
We have a question. What was the application of this device?
Spectrum sensing system, 1 to 18 gigahertz.
We have another question.
We have a bandwidth of 1 gigahertz as the receiver input, and we are down converting it to IF. Why are we actually the purpose, initially the system was planned for 1 gigahertz bandwidth, because the commercial competitors of ours, Agilent, Keysight, there are many, Mountain, Copper Mountain, there are many other competitors that are selling the same equipment. Their bandwidth usually of 1 giga. So we planned for 1 giga, but the problem was we wanted to implement the initial design with 500 mega. So the first IF filter at 22 gigahertz, as I already stated to you, finding high Q filters at those frequencies becomes a difficulty. So we could not find any SMD component for that. Cavity filters were available, stripline, COM. The cavity filters were available, but we could not source any SMD component. The size was to be reduced. So Knowledge is a very good company that that have many SMD components in those frequencies. So yeah, we were bound to that. So at present we use that. I will share the sensitivity later. Give me a minute. So now we will move toward the software application. The software is actually system view. This is pathway system view from similar configurations are if you have experience of Genesis, it is also a good tool to do system level modeling. And I have also seen people working on Microwave Office AWR. It is also a good tool. So when I came to RWR, people were using system view design. So I learned that. So it's all your choices. So when you started the different it's our MATLAB scripting, but the best thing about system view and Genesis is that you can integrate MATLAB scripts into this. You can welcome them here, use them in code, in time domain simulations, frequency domain spectral analysis. I will just close that help. So now it comes to the getting started window. So there are different templates available: data flow template, data flow RF beamforming, linear templates, RF architecture template that we will be working on, RF link template, RF phased array design transmitter. A lot the software can offer. So it opens up a template for better to use a bigger screen, so better visualization. My laptop is small at present. So what you can do is you can have this is the simplest form of an RF chain. At the left side, you have a menu, drop down menu like thing. You have cascaded gain, you can be calculated. This is a schematic capture of the schematic diagram. Then these are the different settings for the source. Like this is the source you can source the setting. Then in fact system data, any simulation you do will be stored in the system data. And any, for example, at present we are using this generic from its library. This is library. This is its library. You have a lot of different parts. GNSS part, GSM parts, hardware, radar, RF. It's a lot of diversity in its part. So even commercial vendors like mini circuits, few of analog devices Texas Instruments, their actual ICs, their non-linear and linear models, it's available in this software. It is to 2021, and if you get a higher up version, they will that will be even better. So if we move towards RF design part, you can see I selected RF design all categories. There are all non-linear models, mixer, inductors, filters, everything is available there for you to simulate. So you have ADCs, amplifiers, and then you have different coax models, a lot of things available for you, splitters, powers. To start with, I will just, for example, I will have this, I have this amplifier, and I know, for example, this is a CW signal, 100 megahertz of frequency and minus 20 dBm its power. I can also change it from the outside, also change from there. You can see this is the source, and CW 100 megahertz at minus 20 dBm. You can click edit, then there you can also change this frequency 100 megahertz. For example, I say, for instance, it's 5,000 megahertz, minus 20 dBm power. You can also have a phase degree, 0 degrees for the when the signal is just starting at t equal to 0. You can have add voice noise, white noise as well. Modulated RF, you will have to give a modulation scheme. Frequency comb means you can have a sweep of frequencies, frequency spectrum. I will switch to at present for simplicity from CW mode. And just click OK. Now the CW mode is ready, 5 gigahertz at 20 dBm. And the gain of this is a generic amplifier. You can also change. For example, you double click that, then you have a gain, noise figure, it's optimal P1 dB, the compression point, the saturation point, OIP2, OIP3, and different. One method is to use this. Then the other scheme could be you can have select as data, then you can give path data for all the components or the amplifiers or the different amplifiers, attenuators, filters. You can have the S parameter files. Any component you use, you can download from the website. You can also import that in this software. Data. You can have touchstone file imported there. You can have Genesis models as well, or Genesis by the way. Then the file name, you can browse and any S2P file like this. This is a low pass data filter. It's file. Usually you have mostly measured data available from the company. If you don't have any for any component, you can fabricate that. You can have a filter. You can measure that on VNA, get the touchstone file and import it into the system view. So you can have as close to as reality based model as you can. So at present I will close this. For example, now if I simulate it, this is the simulation button for this. If I simulate it, now it's simulated. It says how I receive the results. It's also very simple in this. You can just click on this node, add graph. At this point, it will say that, okay, new data power plot. You want to have a power plot, spectral density PSD plot. You want to have a cascaded gain, cascaded noise figure, anything. So first we can have a power plot. But this is the power plot. You can see my original signal in the schematic. The original signal was minus 20 dBm. And the gain was 20 dB. So the output power will be 0 dBm. So I just plot. This is the power plot. It's in the left. This is the power plot. So you can see this is the 500 megahertz, 0.07 dBm. This is the output power. This is its first harmonic. You can see this is the first harmonic minus 36 dBm down. This all you can set in the receiver. Now this is the design. Now I will add a few things to get the noise figure as well. Demonstrate, for example, this was the amplifier. I will add a filter maybe. band pass filter, you can have Chebyshev filter design. It's added there. Now I know that the source frequency is 500 megahertz. I will just say that faults. Insertion loss, I will just say this, these two quantities, for example, I may said that it's centered at 500 megahertz. Its low will be 49,100 megahertz, and I will be 51 just to get the carrier passing through. So rest I will leave the same. So this is the filter, then the amplifier, then maybe we can have a frequency mixer as well. And this is a frequency mixer, you need an LO source as well. So we may have a oscillator as well that will drive this mixer. Since the input frequency is 5 gigahertz and the IF we can have around maybe we can have 500 megahertz. So the LO frequency I will enable as maybe 4500 megahertz. 4500 megahertz. LO power we will have 13 dBm, for instance. And we can again simulate it. One error as usual. So LO. You can also see there is a conversion loss, conversion gain here. You can have it's 7. You can also troubleshoot this in multiple ways. For example, you can click in between this, add new graph, power plot at 0.6. There are different at every point there is a given. For example, for this these two powers. You can see this is the 4500 megahertz. This is leaking from the mixer to the amplifier chain. This 0 dBm power around is 505 gigahertz coming from the source. There is some minor error in the simulation there. You can even short these two using this function. This is the short. Now it is short. You can simulate it again. So error goes. So you can have the power at, for example, this was out point node 2. This is the node 2 function. So it does say that the output power is still around 5 dBm, 500 megahertz. So time is short. I will not troubleshoot that at present, but you can see that this is how a basic model simulation. You can add things later on YouTube. Orang Bagaya something. This is the YouTube channel of the Agilent employee. He's a very senior member, very good, and his tutorials are very good. He has done series, I think hundreds of videos on ADS and system view designs. I'm also a student of this software. I have learned a lot from his videos. We should acknowledge them. And that is the source from my learning as well for this software. So now we will move towards the actual simulation design of. Sorry. Now we will move toward the software, the simulation design of the design that I have shared previously with you. We also show the recent used workspace that was tuned receiver in color. We have incorporated all the standard S2P files from the vendors, and those we could not get from the vendors. Like many filtered and transit models, we measured them and imported them into this the software for analysis. First, I will show you the schematic. This is the chain. Obviously, you can open it on a bigger screen as well. So you have all the components for every chain. This switch is actually just to merge this, the input. You have all this component, the amplifiers, the attenuators, inline. Took a lot of effort actually to get all the idea we have for the chain into the software. This is the switch matrix I was sharing. This is the signal amplification and conditional block I have shared with you. And this is the mixing part. There's the second mixer. Then there is an IF chain parts. Then there's an IF output. Now to start with, first I will share with you the frequency plan that I have already talked about. So you go to design, add. What if frequency planner? Now, what if frequency planner with the same name? I think you can have it in Genesis as well. I think in MATLAB also new versions they are having it. Receiver frequency planning. This is the tool. What actually you have is you can name it. You can have it intermediate frequency at mixer output. Then the spurs, because the spurs are also harmonic dependent. They could be first order, second order, third order. You can have any order. Maybe for example, just I could have 7 orders. That the range or the amplitude range you can have many, but looking at 70-80 dB is enough. For example, 70 dB. Then all intermediate frequencies. Then IF center frequency. What actually are you planning? Since in our design the second frequency is fixed and the first frequency is tunable, so I may say the first one is 22 giga, 22,000 mega. I should just apply, and at the inputs, I would say RF center frequency. You can have your own. In my complete bandwidth was 1 to 18 giga. The center is 9.5 giga. I will just put 500 mega, and the RF bandwidth was 1 to 18. So RF bandwidth is around 17 giga, 17 giga. Then IF bandwidth, as already I have stated, we have checked it. At present, the hardware is working at 500 megahertz. The input drive level you can have 13 in 0 minus 10. The maximum input signal, for example, you can handle. Then the hello drive level could be 13 dBm. Then you can have as already I have stated that we are mixing 1 to 18 gigahertz with 23 to 40 gigahertz. So we have an LO high side injection. The LO frequency is higher than the RF frequency. You can see this as I applied. So IF bandwidth. the error of C. Similar type of tools you will find in Genesis and other as well. The error at present. Now the error has been gone. You can see it also tells you how much will be the value of frequency if you are doing the high side injection. We are doing the high side injection because we would have an overlap with the incoming RFs. But there are complex configuration in super heterodyne as well, where you don't need to go to 40 gigahertz, and you can have a design. People have worked with that as well. So LO frequency will be 23.5 to 39.50 with 1000 mega IF. IF1 centered at 22 giga. So you can see this slot is of attention. Like you can see, these are the spurs, or the spurs we don't want. Of course, these are very high frequencies. We're not interested in that. 30, 40 gigahertz, 37. It's max 50 giga. You can see this one even is falling. It is 3 RF multiplied by mixer into 3 LO. So the relation I was sharing. NFM plus minus MFN MF2. So you can see, you can point IF centered at this frequency, 3 times this, 3 times this. So they do fall in band, but the power is very low. Overall, the this whole spectrum, this band we have selected is clear. So that is how we plan frequency planning for this one. And for instance, another system we have been working on, it was also centered at 22 gigahertz. But its center frequency was, I think, 10 giga. 10 gigahertz. It was around from 2 to 18 giga. So the bandwidth was 16 giga, and the IF bandwidth was smaller. It was 100 mega. If I see this frequency plan, you can also in this frequency plan also. This will also work. So any frequency placement or frequency plan, I am talking about very broadband receiver. Your application could be GNSS or any other. You would be working with very low narrow bandwidths and narrow frequency plans. But this is how it is to be done. And you can see this is valid IF region is this. You won't have any spurs in this region, and this works. So that is from the frequency planning. And now we move back towards the design. Better to use a bigger screen, but for instance, this one was the frequency plan. These are the data sets. You can see these are different amplifier models, different step pattern. This is a step innovators, switches that are used. These knowledge filters. They all, some of them are from the vendor, some of them from the we made ourselves. These are equalizers at different frequencies, couplers. All their files have been put into this software. It was a long task. So we have, and then another thing I want to share in this, an important thing is you can have, for instance, in this configuration. Sorry. In this chain, I have already shared with you. For example, this is the first local oscillator that needs to be tuned. For instance, you are trying to look into 1 to 1.5 megahertz bandwidth. So at that bandwidth, the tuning LO value will be 23.25 gigahertz. You jump to next band, 1.5 to 2 giga, the tuning LO will move to 23.75 giga. So how to incorporate that into software so that you won't have to change the values of LO every time. So for that, we have MATLAB scripts in that. We have LO variation. You can have MATLAB, for example, if the RF frequency is in this range 1 to 1.5, set the LO to this value. If this value, set the value LO to this value. If this value, set the LO to this value. So this is again written in mat as C, written in C in MATLAB script. You have different LO values. Then these codes are, for example, at the input we have divided the 1 to 18 gigahertz bandwidth into 5 different octave bands. So we have different paths to select. So that is the code for that. That if this is the frequency range, select this path. If this is the frequency range, select this path. Because all the things can be managed as variables in this system as well. So that was for this. Then this is the noise figure, simulated noise figure of the system versus frequency. You can see as the frequency increases, the noise figure of the system remains consistent. It is below 4 dB, around at average, I would say 3 dB noise figure. I will also share with you later on the Mayer results, what we have achieved in our fabrication as well. That is the P1 dB, the compression point. When you attach a lot of the components in the chain, you can have a compression point minus 3 dB. Then this is the out spectrum, for example, at one single frequency, 500 megahertz to 1200 megahertz bandwidth filter response as well. And these are the spur response as well if it goes. This is the noise figure response I was talking about. You can see this at the bottom. These are the components, different frequency components. They are added in series. And so at some frequency, I can't figure out, maybe this plot is at a single frequency. You can see the first few components are adding major noise figure contribution to the total overall noise figure of your receiver. After some stage, till the first mix, it becomes constant. So noise figure usually in a receiver, in a heterodyne receiver, will be defined by the first few components. The best you select them, the better noise figure, the better sensitivity you have. And now I will show you the CNF gain plot. Cumulative noise figure. Cumulative noise figure of the chain. At the bottom, you can see the components, different components in line. So that is from the software actually. So that is the other plot I showed you, CNF versus frequency. This is with respect to frequency. And every frequency, the noise figure, because there are a lot of components in the chain, you may have lesser components. So every component has its own. The average noise figure is around 3 dB. Then P1 dB. Then I think that is from this software. Now we'll move towards the Mayer results. Then you can have a better picture. Any question for the respondent? Welcome. So that was from system view. Now we move back towards the slides. This was the frequency plan I was talking about. Then this is the node 1 Mayered gain. We work in nodes. First prototype, second prototype, node 1, node 2. So this was the first node that we made of this hardware. You can see this is a gain variation. Ignore this because these are band crossovers. I already shared you. The first band is 1, 2, 3, 4. These are just crossovers when the switch. So between measurements, so that is these spikes are due to these reasons. So you can see this first the gain variation I was talking about, that your ADC needs an equalized gain. So that is plus minus 3 dB within this range. This is the first node we made. Then this is the second and actually third and fourth node. You can see that the gain center is 50 dB and now it is equalized in 52 to 58 dB, 48 to 52 dB. So we have reduced 2 dB variation. Basically, this is a unequalized gain. This is how it looks like the variation if you don't equalize and work, because since there are a lot of amplifiers working in different frequency bands, everyone has a different gain, everyone has a different noise figure. So at the end of the receiver, when the ADC is sampling, you need an equalized version of that. So how we did that? Because we have different frequency translations. We did that in this design, super hetero design. We did that using attenuators. And the idea was drawn from basic spectrum analyzers in your labs. They also do using DSS, digital step attenuators. The resolution is defined, thus defines how much gain equalization you will achieve. This is a very big band, but it depends upon the application. You might be working on a smaller band. Then this is the P1 dB point. I shared with you that at this point, the receiver just saturates. Does saturates, but this is not the maximum input level. After this point, the FPGA adds higher attenuation levels. Adds higher attenuation levels, then you define a maximum level. I will share a plot for understanding. For example, this one was the noise figure for the first node we made. I earlier shared with you that this was the first one. What went wrong in this? The amplifiers were good. The selected amplifiers, the models they incorporated, they were good enough. But when hardware got fabricated, after a few minutes of operation, it would heat up because there was no thermal mechanism for that to remove the heat. So the noise figure that was intended to be 4 or 5, it would reach, you can see that it was in a range of 7 to 13. So 7 to 13, the noise floor KTB, if you do, you can detect around minus 72, 74, maximum 74, 73, minus 73 dBm level. Then this is the Maillard noise figure of the improved node. You can see that at average it's below 4. That means it can detect a signal at an RF at the receiver, and the receiver, the noise floor will be around minus 80, 81, 83 dBm till. It's a very broad band, so at average was around minus 82 dBm signal detection. Then this is the plot for your understanding. You can see this is the instantaneous dynamic range. When was our noise floor, minus 85, 84 dBm at 500 megahertz bandwidth. You add up the gain, you jump up first gain without any major attenuation. You jump up to this is the instantaneous dynamic range, around averaged at around minus 40, maybe minus 35, 37 dBm. Then you increase the attenuation levels further. Increase the attenuation levels further, then that is total dynamic range. That is for a single carrier. When you measure it with two carriers at the same time, then what happens is two carriers at the same time but at different power, they do intermix. Then you have SFDRs, first dynamic range at this much power. That is also parameter you may do receivers. So that is the version, the first, the improved version. It's in trials with the customer at present. It has a very good response. 1 to 18 gigahertz input. We actually the customer requirement was input 1 to 8, so we used a solid state or a mechanical switch at the back, merged the inputs to 1 to 18, and then send it to, because whatever customer says, you have to do this. Okay? So this was our first from a product from my team. This was the first one. Then just a small example of another product that I have been working on. This is a 0.1 to 1 gigahertz receiver. This is particularly for comment applications. So you can see this is also super heterodyne architecture. This is amplification and gain control. This is the frequency translation part where you actually translate 0.1 to 1 giga to 2 giga 50 megahertz. Then you mix it with 3 giga to 2 giga to 3 giga frequencies. So then you have an IF stage. Here we have used PLDRO, phase log dielectric resonator oscillator, for better phase performance. And this is the heart of the system, tuning LO, that actually produces different frequencies. It is programmed. This is the final fabricated version of this. We do everything in RWR. We have a very good facility, from gold plating, tin plating, PCB laser fabrication, component sourcing. This is the hardware we fabricated for a customer. You can clearly see these ridges these are for EMI RF, EMCMI gaskets. They also take care of EMCMI gaskets. Just for an overview, this is the gain variation of an unequalized gain. You can see how much variation it is. This is all the noise figure for this, less than 3. Then finally, that's all from my side. We do a lot of things at RWR related to RF microwave systems, digital systems, PLL. So these are different contributions from my side to the company. We do gold plating, in-house gold plating, in-house gold plating of the components, complex antenna. This is a Hoghorn donors antenna, spiral antenna, so modern application. This is a 23 gigahertz divider, 6-channel symbol log periodic. These are the circuits. We do simulation in ADS, then import models into Altium or CST for mechanical and different applications. This is I was sharing with you tuning LO 23 to 40 gigahertz. This is a notch for some applications. So that is what I do. Now, final any question or answers?
Thank you so much, Hassan, for a very insightful lecture. In fact, it is high level of commitment. We actually spoke non-stop for almost 3 hours. And I thank the audience for attending, both the online and the ones who are present over here. I hope that you have gained valuable insight. So we'll conclude the session since there are no questions. Before concluding the session, we would like to ask you guys to please share your screens, turn on your cameras and share so that we can take a picture, please. If you could please turn on your cameras, speak on your audience. You take the picture now, please. Yes. Yes. We conclude the session. Thank you so much.